Okay. So the key thing here is going to turn out that we have to manage this sample error. And so, yeah, did I skip this? I must have skipped this slide. Okay, so the rank of this sample is m-1, where m is the size of the ensemble. So we lose 1 degree of freedom to the mean. And this is very small compared to the number of state elements. So the number of state elements, like Eugenia said yesterday, is at least on the order of 10 to the 7 for weather, climate, and ocean models. Whereas we're using ensembles of size roughly on order 100. So how can this possibly work? How can we estimate 10 to the 7 degrees of freedom with 10 to the 2 samples? And so a mathematical view about why this works is that the singular value spectrum of B is very steep. The singular values are compressed in a relatively narrow subspace of that matrix. And that's because, if you think physically about this problem, that there are strong correlations in the state. If the state elements were uncorrelated, we'd be in bad shape. We'd have a real problem. The fact that the temperature here in Kobe correlates with the temperature in Tokyo and over the Western Pacific on hundreds to perhaps thousands of kilometers means we have a large portion of the subdomain that's related to a measurement we may make at one location. So that's a really, really powerful property of the system that we may not know about unless we understood the physics of the system. Another way to look at this, you talked about Lyapunov exponents and Lyapunov vectors yesterday. And I think you did for Lorenz 63. You found that one Lyapunov exponent that's growing. There's one 0. And because volume elements are conserved for that attractor, they have to sum to 0. Well, if they're summing to 0, and one of them is 0 and one of them is positive? Negative?
Volume contracting. I mean, the dimension of the attractor is smaller than.
But the volume of the attractor is not changing, right? The basin of attraction is fixed. So for any individual...
It's volume contracting.
Sum of the exponent is approximately 1 plus 0 plus minus 14.
The divergence of the vector field is negative.
For that particular system.
Yeah, that's right. Yeah, for the typical parameters, you're right. It's 1, 0, and minus something big. Okay. Thank you for the correction. In any case, I think it's at least an empirical fact that the Lyapunov exponents also have a steep spectrum. And so what this means is if you can do these experiments with models including Lorenz 63, you can put random noise onto the initial state. And you can run it for a long period of time. And what you find is that initially a lot of the error decays. Right? So you get this drop in the error, and then it starts to grow very fast, approximately exponentially, before nonlinearity becomes important. And what's happening there is that it's dominated by decaying degrees of freedom. So it's projecting mostly on directions that decay, and it's only until the stuff that had a small projection starts to grow and show you the leading Lyapunov exponent that you get the stretching along those limited degrees of freedom. All this is to say that, again, the system is not as high dimensional as it might seem. Okay, but nevertheless, we still have to manage the error. And we have essentially two sources of difficulty. One is due to the fact that we have, at long distances, we have errors in the covariance. So just by random chance with a finite sample, if we try and estimate the covariance between two remote points, we may get a relationship where there is none. So if we have a way of removing those, we effectively boost the rank of that matrix. We're essentially zeroing out the off-diagonal elements of that matrix. So we don't expect the temperature here in Kobe to be related to the temperature in Antarctica. By random chance with a small sample, we will find a non-zero relationship. If we zero that out, we've effectively boosted the rank of that matrix. And that's important because although we have no guarantee about whether a measurement will make our skill or bring our state closer to the true state or take it further away, we are guaranteed that it will remove variance from the system. So that's negative definite. Every time we assimilate a measurement, it shrinks the variance. So if we take some out inappropriately, we can't get it back. And so this can lead to things like filter divergence, where we can decouple from the measurements because the variance becomes too small in the analysis. It persists too small in the forecast. We put more weight on the background, and that process cascades. So, a useful measure, and I highly recommend to anybody using these tools that you get in the habit of computing this thing. This was originally due to Murphy in a paper in the late 1980s. Some basic statistical properties of ensembles. If you compare the ratio of the expected error in the ensemble mean, so if we take the mean of the ensemble and we have a way to verify it against measurements, and then we take its expected value over, in principle, the whole attractor, that gives us the numerator of this ratio. And then if we look at the average or expected value for the variance, and the denominator, that should go like m plus 1 on m, where m is the size of the sample. So for reasonably sized samples, these two things should essentially be the same. The error we have in the mean should match the spread that we get. What we often find in practical problems is that there's too little spread in the ensemble, and we have to inflate that. So this ratio is often, but not always, greater than 1. So it's a good thing to compute this for your prior, but you can also compute it for the posterior if you withhold some measurements from the data assimilation, if you have an independent way to verify this thing. Or it's very common to do this in the background at the 6-hour forecast, say. So we can correct this situation in several ways. One is by blending the dynamic forecast covariance with another source, such as from climatology, or we essentially dress the covariance with something that stabilizes this. And the other one is to use multiplicative inflation. So we remove the mean, and we multiply the ensemble perturbations by some factor to make them larger. If we use a fixed scalar, that's okay if, in some sense, the observations and the dynamics are uniform. We get into trouble if we have places that are not well observed because we can overinflate the variance, and it can run away if we don't have a way to constrain that. And that's given rise to adaptive inflation schemes. A very nice paper by Dakimasa showing us how to do this in a relatively cost-effective way. Shows if you do this adaptively, you see that this factor depends upon the observing network. And so on average is perhaps close to 1. The red values go from, so whites are around 1. Those of you in the back of the room, the darker reds are about 1.3, and the blues are actually deflation. We're deflating the variance in the ensemble. So some places get the spread made a little smaller. In any case, it's something we have to take care of. With ensemble square root filters, one way to do the solve is to process the observations one at a time. This can be very convenient for the error covariance localization process. So we have a measurement, we know where it is, we know what its covariance with the state is, and we can apply a localization function in a very straightforward way for that situation. So that's one of the main reasons why that's popular. And when we use that, we're also using something called the augmented state vector approach. So this may have been touched on yesterday, I think, in the practical session, I'm not sure. We can, in addition to the state elements, we can augment our state vector with an arbitrary number of parameters, including the estimates of the measurements themselves. So as we walk through the list of measurements one at a time, we can update all of the other measurements that we're going to use as we walk down the list. And this avoids needing to compute their measurements every time we've assimilated one of these measurements. And this is especially useful if it's an expensive exercise to compute the measurements. We compute them all up front at the start. We augment our state vector with all of these estimates of the measurements, and then we update all of those estimates with the ones that we assimilate one at a time. And that's essentially equivalent to, after assimilating a measurement and updating all the ensemble members, running the H operator over the updated ensemble for the next measurement. You can do it both ways, but in principle, this augmented state vector is a cleaner approach. But you don't have to do that. All right, so let me talk for a moment about offline and online data assimilation. Online is basically what you've heard about so far, this notion of cycling, sequential data assimilation, where the prior is coming from a forecast from an analysis we had some relatively short time period beforehand. Because for weather and ocean prediction, these forecasts are extremely accurate. They give us very accurate estimates of the measurements that we're going to assimilate at the next time. So this is very, very useful if the model has skill. We're not always in that situation. And even when we are, I think there's a lot of benefit to doing offline data assimilation. So for offline data assimilation, the prior doesn't come from a forecast in the past state. It comes from some other source. So I'll be talking about the Paleo Climate problem. We don't have the ability to cycle Earth system models for thousands of years for 100-member ensembles. For one thing, it's computationally prohibitive. For another thing, they have very little skill on the timescale resolved by these proxies. So we're essentially sampling the climatology of the model. So why not just do it with a single long simulation, which is what we do. Yes, there was a question or a comment.
Yeah, I'm a little confused as to what you mean by skill.
Yes, by skill I mean if you compare the forecast with a reference source like the climate, the stationary climate, that there's some difference there. There's meaningful difference. So if we compare a weather forecast 6 hours from now with the climate statistics, we could say that we have a lot of skill relative to a random draw from climatology for January 24th. On the other hand, if we make a weather forecast for January 24th, 2019, we expect the distribution to be the same as the climate. We have no skill relative to that reference source. Any other questions, as long as I've paused? Okay. One of the main reasons I got into this is I found that my students were getting hung up and burned out on trying to get models which are often brittle in this step. So let's face it, when we're doing data assimilation in a sequential fashion, not necessarily in 4D VAR with the strong model constraint, but we're often taking the model off the attractor, off its attractor, right? These measurements are pulling the model somewhere else where it doesn't want to be, and then they'll often gracefully come back down onto their attractor, but sometimes not, right? And so you can get into a lot of frustration trying to deal with that problem. So offline is very useful because you don't have that problem. You can examine your data assimilation algorithm without the risk or the headache or the overhead or the expense of generating these model forecasts. So I highly recommend starting here if you can. It's a useful starting place, even if you're doing the problem on very short timescales where your model has a lot of skill. You can use priors from, say, an operational existing forecast model and test what a new observation might do. And then you can compare that with the online case. Okay, so that marks the end of the primer part of the lecture. I guess I've gone quite fast because I have time actually to talk about coupled atmosphere ocean data assimilation. So before I dive into this, there are questions about the basics? Yes, sir.
Can you go back to how, I don't understand how multiplicative inflation works. I don't know what you, how you do that.
Right, so this one is the simplest one, this fixed scalar. So we have our ensemble, let's say, to fix numbers, we have 100 ensemble members for the full state, the weather prediction, right, or whatever it happens to be. We remove the ensemble mean, and then we have deviations from the ensemble mean. we can simply multiply those deviations by a fixed number, 1.1. Boom, out they go. And like I said, that can be okay. It can also be problematic. We might want to do something smarter and use the measurements and maybe this ratio as a way to guide how much we should be inflating or how much not, right, relative to the measurements that we have and the errors that they have. Does that make sense?